Since the beginning of time, humanity has dreamed of outrunning the distances that separate us from the stars. The night sky, scattered with suns and galaxies, is a constant reminder of our smallness, and yet also of our ambition. When our ancestors first looked up, they saw not just points of light, but destinations. Each star became a challenge, each constellation a map to a place that seemed impossibly far. To cross those gulfs was unthinkable, but to imagine it was irresistible. Stories of flying chariots, divine steeds, and celestial pathways filled ancient myths, because the yearning to travel faster than nature allows has always been part of us. For most of human history, speed was measured by the gallop of a horse or the sail of a ship. These were impressive in their time, but even the swiftest rider or the fastest vessel barely scratched the surface of Earth's horizons. The invention of machines brought new leaps. Steam carried us across oceans. Railways tied continents together. Airplanes lifted us into the skies, and rockets finally tore us free of gravity's grip, hurling humans into orbit and machines beyond the planets. Each step was a victory, each new record a declaration that speed could be conquered. But with each advance came a deeper realization. No matter how powerful the engine, no matter how efficient the fuel, the distances of space dwarfed our progress. A rocket could circle Earth in hours, but to cross to the nearest star would take tens of thousands of years. The dream of faster travel was not enough. Something fundamental was holding us back. That something was gravity, the unseen ruler of motion. Gravity is not just the force that keeps us on the ground or guides planets around the sun. It is the very architecture of space-time itself. It sets the stage on which every movement occurs, and it dictates the limits of what is possible. Gravity curves the path of light, slows the ticking of clocks, and anchors every galaxy in the cosmos. When Einstein revealed that gravity is not a force in the traditional sense, but the bending of space-time, he also revealed its power as nature's absolute governor. It is not negotiable. It is not a rule we can choose to ignore. Gravity defines the playing field of motion, and within that field, the speed of light is the boundary line that cannot be crossed. Yet science fiction has always rebelled against boundaries. From the pulp adventures of the early 20th century to the sleek visions of starships streaking across galaxies, fiction dared to imagine that faster-than-light travel was not only possible but practical. Warp speed became more than a plot device. It became a symbol of defiance against the tyranny of distance. The idea that a ship could bend space itself, contracting it in front and stretching it behind, was intoxicating because it seemed to sidestep the very laws of physics. If gravity ruled motion, warp speed promised rebellion. If Einstein set the limit, warp technology proposed a loophole. The ultimate race through space was no longer between rockets or engines. It was between gravity, the enforcer of cosmic law, and warp speed, the dream of escaping it. The contest is not simply technological, it is philosophical. On one side stands gravity, proven, universal, and unyielding. On the other side stands warp speed, speculative, untested, and tantalizing. Which will prevail? Will humanity forever be bound by gravity's laws, exploring the stars only slowly, with journeys measured in millennia? Or will a future breakthrough in physics unlock warp travel, collapsing distances, and making the galaxy accessible in lifetimes? To answer this, we must first understand the rules of the game. For before we can pit warp against gravity, we must know what each truly demands. Speed has always been more than convenience. It is power. In every age, those who mastered faster movement reshaped the world. Armies that marched quickly could outmaneuver enemies. Ships that sailed faster could dominate trade. Nations that built faster machines could project influence across continents. Speed has never been neutral. It has always been an advantage, and in the cosmic theater, it becomes the ultimate advantage. To move quickly through space is to expand the reach of civilization itself. But the farther we stretch our vision beyond Earth, the more we encounter the reality that nature has already written the rules of the race. Gravity is the most relentless of referees. It does not care about our ambitions or our imagination. It warps space-time itself, shaping every possible path. On Earth, we feel it as weight, the tug that grounds us. In orbit, we feel it as freedom, though in truth, orbit is not escape, but a delicate fall, a constant dance around the planet. On larger scales, gravity sculpts galaxies, curves light into arcs, and holds clusters together across millions of light years. Everywhere, gravity rules, not with force alone, but with geometry. It shapes the roads we travel before we even set out. It bends light, it slows clocks, it stretches time near massive bodies. It is both invisible and absolute. Against this backdrop, the human dream of faster travel becomes more audacious. Rockets gave us escape from Earth's pull, but gravity never left the story. Every trajectory, every orbit, every mission is a negotiation with gravity's field. To reach Mars or Jupiter or Saturn is not to break free of gravity, but to ride its curves, to slingshot around planets, to borrow momentum from celestial bodies. Gravity assists are reminders that speed is never ours alone. It is always a gift of space-time's shape. The faster we go, the more we see how gravity sets the terms. And yet, there has always been rebellion in imagination. The storytellers of science fiction looked at gravity's authority and asked, what if we could cheat? What if the laws of Einstein, however elegant, were not absolute? What if the cosmos allowed secret doors, shortcuts hidden in the folds of space-time? Warp speed was not born of mathematics, but of longing, a yearning to cut through distance as if it were nothing. It captured the idea that while gravity might govern the game, cleverness might find a way to play outside its rules. The warp bubble, the starship streaking faster than light, was the declaration that gravity could be challenged, that Einstein's speed limit could be skirted by bending rather than breaking. The contrast is stark. Gravity is cold, impartial, and tested across every observation. It has no mercy for wishful thinking. Warp speed is warm, imaginative, and untested, a vision painted across the canvas of fiction. But history has shown that imagination often leads science. Heavier than air flight was once impossible. Splitting the atom was once unthinkable. Traveling to the moon was once fantasy. Each became real because imagination persisted until technology followed. Warp speed remains in the realm of speculation, but its persistence in culture is more than entertainment. It is pressure on science itself, a constant reminder that the race is not yet decided, that perhaps even gravity can be outplayed. To weigh these contenders properly, we must understand them deeply. Gravity is not just a force, but space-time curvature. Warp is not just a story, but an idea given mathematical form. The ultimate race cannot be judged by appearances. It must be judged by physics. To understand who wins, we must move beyond dreams and into the laws that bind or free us. And so, the first step in this contest is clear. Before we imagine warp's challenge, we must know the full power of gravity, the champion that has ruled motion since the birth of the universe. The dream of warp speed is seductive because it promises to undo the tyranny of distance. Imagine leaving Earth and reaching Alpha Centauri, not in tens of thousands of years, but in days or weeks. Imagine voyages to distant galaxies, not for generations unborn, but within a single lifetime. This is the vision that has propelled countless stories, filling theatres and novels with the sound of engines roaring beyond light. It is more than escapism. It is an assertion that the human spirit cannot be bound, that the vastness of the cosmos is not a prison, but a frontier. Warp speed embodies hope, rebellion, and the possibility that nature's limits are not final. But hope alone cannot rewrite equations. When Einstein revealed the structure of space-time, he did more than place a speed limit on matter. He unified the laws of motion and light, making the speed of light not just a fast velocity, but the very scaffolding of reality. The geometry of relativity is not a suggestion. It is the architecture in which every law of physics resides. To surpass it is not like breaking a speed limit on a highway. It is like asking to travel faster than causality itself, to overtake the unfolding of events. That is why gravity, in Einstein's form, has no rival. It is not just a force among others. It is the framework of all. Warp speed enters this story as a challenger, not by denying the framework, but by twisting it. The Alcubierre drive, when it was proposed in the 1990s, showed that within Einstein's own equations there was a loophole. A ship might never exceed light speed within its local frame, but space itself could expand and contract, carrying the vessel faster than light relative to distant stars. It was a breathtaking insight. Relativity's own geometry could be used against itself. The dream of warp speed stepped from fiction into the edge of theory. Yet it came with impossible costs, demanding exotic negative energy beyond anything we know. Warp speed, for now, remains an idea without substance, a mirage glimpsed in mathematics. And so, the race is set. On one side stands gravity, the undefeated champion of the universe, tested in black holes, in pulsars, in the bending of starlight, and the ticking of atomic clocks. On the other stands warp speed, a dream half rooted in physics and half in longing, a challenger that has not yet entered the ring. The question is not trivial. To compare them is to ask whether the universe is bound forever to Einstein's horizon, or whether some future physics will open doors we cannot yet imagine. The contest is not only between what we know and what we hope for. It is between certainty and possibility, between proof and imagination. As this first chapter closes, the stage is set. Humanity's dream of faster-than-light travel collides with gravity's immutable rules. The ultimate race through space is not decided by engines or rockets, but by the deepest laws of reality. To understand who wins, we must examine each contender closely. And the first is gravity itself, the quiet, relentless power that has ruled the universe since the beginning of time. Gravity is the oldest force we have known and the last we truly understood. To the ancients, it was the invisible hand that pulled stones to earth and guided planets across the heavens. To Newton, it became a universal law, a force reaching across infinite space, binding suns and planets with an elegance of numbers. For centuries, this vision ruled without challenge. But in the early 20th century, Albert Einstein shattered it with a revelation more profound than any before. Gravity, he declared, was not a force at all. It was geometry. In Einstein's general theory of relativity, space-time itself is flexible. Mass and energy do not merely exist within this fabric. They shape it, curve it, bend it, and in turn, the curvature of space-time dictates how matter moves. Planets orbit not because they are tugged by a distant force, but because the space around the sun is curved, and the straightest possible paths, the geodesics, loop into ellipses. Light bends around stars not because it has weight, but because space-time itself is distorted. Gravity, in this vision, is the stage and the script. It is not something within the universe. It is the universe's very architecture. This new understanding transformed not only physics, but philosophy. It meant that space and time were not absolute, not rigid containers in which events played out, but dynamic entities intertwined with matter. A clock on Earth ticks differently than a clock in orbit. A ruler near a black hole measures distance differently than one far away. Time dilates, space stretches. Reality itself becomes relative, dependent on position and motion. Gravity is no longer a background player, but the director of the cosmic drama. The power of this insight is visible in the most extreme places. Black holes are not merely objects of immense density, but regions where space-time curves so intensely that no path can lead outward. The event horizon is not a surface of matter, but a boundary in geometry itself. Inside, time and space exchange roles, and all roads lead to the singularity. Gravitational time dilation means that near such horizons, time slows to a crawl relative to distant observers. A star spiraling into a black hole appears to freeze at the horizon, its light redshifting endlessly as time itself stretches. Gravity does not merely move objects, it reshapes reality, altering the very flow of time. Einstein's equations, confirmed again and again, show gravity's authority over the cosmos. They predict the precession of Mercury's orbit, the bending of starlight measured during eclipses, and the slowing of time measured by atomic clocks at different altitudes on Earth. They predict gravitational waves, ripples in space-time itself, now observed directly by detectors sensitive enough to measure distortions smaller than a proton. Every test has confirmed relativity's vision. Gravity is the sculptor of the universe. Yet there is a boundary even gravity respects. No matter how curved space-time becomes, no signal can travel faster than light. Black holes form horizons defined not by mass alone, but by this limit, beyond which no escape is possible. Gravitational waves themselves travel at light speed, carrying news of cosmic collisions across billions of years. The speed of light is not simply fast. It is the limit written into the fabric of geometry. Gravity, mighty as it is, does not break this law. It enforces it. And here lies the heart of the contest. Warp speed imagines bending space-time in ways that allow travel beyond this boundary. Gravity already bends space, already stretches time, already creates shortcuts through wormholes. But it never allows violation of the cosmic limit. Gravity's power is absolute, but its loyalty is to light. To imagine warp speed is to imagine a challenge from within the very equations Einstein wrote, a loophole hidden in the rules. Before we can weigh such speculation, we must fully understand the champion that already rules. Gravity is not a force to be beaten. It is the very game itself. Gravity is the quiet architect of the universe. We rarely feel its grandeur because we live within its embrace, like fish unaware of the ocean that carries them. Yet its reach is infinite, and its effects define the largest structures in existence. Every star that burns, every planet that orbits, every galaxy that spins owes its coherence to gravity's guidance. It is the cosmic glue, invisible yet relentless, patient enough to build galaxies and merciless enough to collapse them into black holes. One of gravity's most extraordinary powers is its control over time. In Newton's universe, time was absolute, ticking the same everywhere. Einstein showed otherwise. Time flows differently depending on the depth of a gravitational field. Near Earth's surface, a clock ticks imperceptibly slower than one in orbit. The difference is so subtle that only atomic clocks can reveal it, but it is real and measurable. In stronger fields, the effect grows dramatic. Near a neutron star, seconds stretch into minutes compared to observers far away. Near a black hole's horizon, time slows to a near standstill. What we call time dilation is not illusion, but reality. Gravity bends not only space, but the very rhythm of existence. Gravity also bends light itself, turning the universe into a lens. When starlight passes near a massive object, its path curves, revealing the invisible sculpting of space-time. This bending was first confirmed in 1919, when starlight during a solar eclipse appeared displaced by the sun's gravity, matching Einstein's prediction. Since then, gravitational lensing has become one of astronomy's most powerful tools. Entire galaxies act as lenses, magnifying and distorting the light of objects behind them. Rings and arcs of light across the sky testify to gravity's control over photons. It is not merely mass that shapes light. It is space-time itself, warped into cosmic optics. On the grandest scales, gravity builds structure. In the aftermath of the Big Bang, matter was nearly uniform, sprinkled with tiny fluctuations. Gravity amplified these ripples, drawing matter together into clumps that grew into galaxies and clusters. The cosmic web of filaments stretching across billions of light years is gravity's masterpiece, a tapestry woven from dark matter and ordinary matter alike, Without gravity's patient pull, the universe would be a thin mist, devoid of stars, planets, and life. Every sunrise, every world, every heartbeat is possible only because gravity sculpted chaos into order. Yet gravity is not only creative, it is destructive too. The same pull that gathers matter also drives collapse. When a massive star exhausts its fuel, gravity crushes it into a neutron star or a black hole. No known force can resist it at those scales. The result is an object where space-time curves into extremes, where our equations predict singularities, places where density and curvature become infinite. Whether these singularities are real or illusions of incomplete theory remains one of physics' deepest mysteries. But the fact remains, gravity pushes matter and geometry to their limits, demanding answers beyond what we yet know. Through all of this, one principle holds constant. Gravity respects the cosmic speed limit. Nothing it does, no matter how violent or elegant, allows motion faster than light. The collapse of a star, the ripple of gravitational waves, the bending of light, all obey the same ultimate law. This is not a weakness, but a signature of consistency. Gravity and light march together, bound by the geometry they share. The speed of light is not just a number, it is the thread that ties the universe's fabric together, and gravity, for all its power, is woven from the same cloth. To challenge this is audacious. Warp Speed dares to imagine bending geometry differently, creating shortcuts where gravity offers none. But gravity is not easily challenged. It has passed every test, from planetary motion to pulsar timing to gravitational wave detection. It is universal, impartial, and undefeated. Before Warp Speed can be taken seriously, it must face this champion, a power that shapes time, light, and structure itself. Gravity is not only a player in the cosmic drama, it is the stage itself. Other forces may be stronger in specific contexts. The electromagnetic force shapes atoms, the strong force binds nuclei, the weak force governs decay, but none of them define the architecture of the universe. Gravity does. It extends without limit, linking galaxies across billions of light years, dictating the paths of stars, and sculpting the fate of the cosmos. It is impartial and absolute, caring nothing for scale or circumstance. Whether it is a feather falling on Earth, a comet streaking through the solar system, or light curving around a cluster of galaxies, gravity governs with the same unwavering rules. The universality of gravity is both elegant and humbling. Every experiment, from the falling of an apple to the timing of pulsars, affirms Einstein's vision. Clocks slow in stronger fields. Light bends along curved paths. Waves of space-time ripple outward from cosmic collisions at precisely the speed of light. The predictions of general relativity have been tested again and again, and always they are confirmed. Gravity does not guess, it dictates. In its silence lies authority, in its invisibility lies inevitability. There is no corner of the universe untouched by its reach. And yet, in all its power, gravity does not break the rules it enforces. It bends space, but not beyond the bounds of light speed. It slows time, but never reverses it. It shapes horizons, but never allows signals to escape beyond them. Even in its most violent expressions, black holes merging, neutron stars colliding, gravity respects the universal boundary. The waves that carry news of these events cross the cosmos at light speed, never faster, never slower. The cosmic speed limit is written into the geometry itself, and gravity is both its enforcer and its proof. This is the paradox we now face. Gravity, the supreme power of the cosmos, bows to the same limit as everything else. It curves and sculpts, but never violates. For humanity, yearning to cross the gulfs between stars, this is both reassuring and devastating. Reassuring because the rules are consistent. Devastating because the rules forbid the dream of outrunning light. If even gravity cannot cross that boundary, how could we? And yet, the human spirit resists. The idea of warp speed emerges not as fantasy alone, but as speculation born from dissatisfaction with limits. If gravity bends space to hold planets in orbit and to shape galaxies, then why could it not bend space in a way that shortens distance itself? If space-time can be curved by mass, why not by design? The Alcubierre drive proposes precisely this, not breaking the speed of light, but moving space itself, creating a bubble where the laws of relativity are twisted in our favor. But before we can ask whether warp speed can succeed, we must confront the rule it challenges. The cosmic speed limit is not a suggestion. It is the foundation of relativity, the thread that ties matter, energy, and geometry together. To test warp speed's promise, we must first understand why light speed is the line that gravity and everything else in the universe cannot cross. Every race has a finish line. For the universe, that line is the speed of light. It is not simply fast, it is absolute. Light does not merely travel at nearly 300,000 kilometers per second. It defines the structure of space-time itself. When Einstein unified space, time, and motion, he revealed that light speed is not a number to be surpassed, but a boundary woven into reality. Nothing with mass can ever reach it, and nothing can ever exceed it. The cosmic speed limit is not imposed by convention, but by the very geometry of existence. To see why, we must step into relativity's equations. In Newton's world, acceleration required force, and with enough force, there seemed no limit to speed. But Einstein showed that as an object with mass approaches light speed, its energy requirements grow without bound. Each increment closer demands more energy than the last. At 90% of light speed, the mass of the object appears doubled to an external observer. At 99%, it appears more than 7 times greater. At 99.99%, the energy needed to push it higher becomes astronomical. The mathematics is merciless. To reach the speed of light itself would require infinite energy. And infinity is not available in the universe. This principle is not just theoretical. Particle accelerators test it every day. In machines like the Large Hadron Collider, protons are hurled around rings nearly the size of cities, boosted to energies trillions of times greater than chemical reactions. These protons reach speeds so close to light that their deviations are measured in fractions of a percent. Yet no matter how much energy is pumped in, they never cross the line. They grow heavier, their kinetic energy soars, but their velocity asymptotically approaches light speed without ever touching it. Nature enforces the limit with unyielding precision. Even massless entities, like photons, reveal the rule. They travel at light speed because they have no rest mass, but never faster. This speed is not chosen. It is inherent, a property of space-time's structure. When gravitational waves ripple outward from merging black holes, they too travel at this speed, not above, not below. Light speed is the universal constant that ties all signals together, ensuring causality, preserving order. It is the pace at which the universe itself updates its information. The consequences are profound. Because no information can travel faster, cause and effect remain preserved. If one event influences another, the influence must lie within the light cone, the region of space-time that light can reach. This prevents paradoxes, prevents effects from preceding causes. Without the speed of light as boundary, time itself would unravel. Relativity ensures order, not only in physics, but in logic. Faster than light travel is not just a challenge to engineering, it is a challenge to causality itself. Yet this boundary does not stop imagination. We see it as a finish line, and so we long to cross it. Science fiction proposes warp drives, hyperspace tunnels, and wormholes, all ways of dodging the rule rather than breaking it. The Alcubierre metric does not accelerate ships beyond light. It moves space-time itself, expanding behind, contracting ahead. Wormholes do not cross space faster than light. They shorten the distance. Each idea bends the rules, but does not openly violate them, because to do so would topple the entire structure of relativity. The cosmic speed limit is not just law, it is the spine of reality. For humanity, this means the dream of interstellar travel is bound by a cruel truth. Even at speeds close to light, distances are immense. The nearest star system would take years. The farthest galaxies would take lifetimes beyond count. Gravity respects this limit, light defines it, and relativity enforces it. To imagine warp speed is to imagine a loophole, but before we can weigh that dream, we must explore this limit in full, see how deeply it is written into space-time, and why breaking it would unravel the universe itself. The universality of the cosmic speed limit becomes clearest when we examine the most powerful events in the universe. When two black holes collide, the violence unleashed is beyond comprehension. Masses greater than entire stars spiral together, their horizons twisting, their energy released as ripples in space-time itself. These ripples, called gravitational waves, stretch and squeeze the universe as they pass, carrying news of the collision across billions of light years. One might expect such titanic forces to break all bounds. Yet even here, the waves travel at the same speed as light. No faster, no slower. This equality is not coincidence. Light and gravity are woven from the same fabric. Both are expressions of space-time geometry. Photons are the messengers of the electromagnetic field, massless particles riding along the structure of space-time. Gravitational waves are oscillations of the structure itself. That they share the same velocity is a profound clue that the speed of light is not just a property of photons, but of space-time's very nature. It is the rate at which information can propagate through the universe, whether that information is carried by light, gravity, or any other interaction. The discovery of gravitational waves confirmed this unity. Detectors like LIGO and Virgo measured tiny distortions, smaller than a fraction of a proton, as space-time rippled. The waves arrived exactly when expected, consistent with light-speed travel from their distant origins. The fact that no delay was found, no deviation from the speed of light, was a triumph for relativity. Even the most extreme events respect the limit. The cosmos whispers the same message through every channel. The boundary is universal, unyielding, and absolute. To understand why this is so, consider how relativity ties space and time into one inseparable fabric. The speed of light defines how they convert into one another, how distance becomes time, and time becomes distance depending on perspective. If information could travel faster, the balance would shatter. An observer could see effects before their causes, messages could arrive before they were sent, time order would dissolve, and causality would collapse. The limit is not arbitrary. It is the safeguard that keeps the universe coherent. This truth grows sharper as we explore near-light speeds. Objects accelerated to extreme velocities do not simply move faster. They undergo transformations in time and space themselves. Length contracts along the direction of motion. Time dilates, stretching for the traveler compared to those left behind. These effects, strange as they seem, have been tested and confirmed. Muons created in the atmosphere live longer when moving near light speed. Astronauts orbiting Earth age slightly less than those on the surface. The cosmic speed limit is not just about velocity, it is about how reality itself reshapes to enforce the rule. Even black holes, the most extreme expressions of gravity, demonstrate the law's authority. The event horizon is defined precisely by light speed. It is the boundary where escape velocity equals the speed of light. Inside, no path leads outward, because to escape would require outrunning light itself. In this sense, black holes are monuments to the cosmic speed limit. They are regions where the geometry of space-time bends so steeply that the limit becomes absolute confinement. No matter the energy, no matter the force, nothing can cross outward once inside. Gravity bows to the rule, and in bowing it enforces it. This relentless consistency is why physicists approach faster-than-light travel with such caution. To propose it is not merely to challenge a number, it is to challenge causality, coherence, and the very structure of space-time. And yet, curiosity persists. If the cosmic speed limit cannot be broken, perhaps it can be bent. Perhaps there exist loopholes, not violations, but workarounds, where space-time itself can be reshaped to make distances shorter. This is where warp theory enters the stage, whispering that the laws may allow tricks within their boundaries. But before we explore those loopholes, we must first accept how deeply the cosmic speed limit is etched into the fabric of reality. The cosmic speed limit is not simply an obstacle to human ambition, it is the backbone of reality. Without it, the order of cause and effect would unravel. Imagine sending a message faster than light. In one reference frame, it would arrive before it was sent. In another, it could appear to move backward in time. Such violations are not curiosities. They are catastrophes for logic itself. A universe where information outruns light is a universe without consistency. The limit, therefore, is not cruelty, but necessity. It is the safeguard that preserves the coherence of events, the invisible thread that ensures history makes sense. Every attempt to approach the limit reveals its absolute nature. In particle accelerators, protons are pushed with staggering energy, but the closer they get to light speed, the more their momentum translates into mass-like energy rather than velocity. They grow heavier, their inertia immense, their speed asymptotically approaching the limit without ever reaching it. In astrophysical jets, matter streams from black holes at velocities just under the speed of light, but never beyond. Gamma-ray bursts, among the brightest explosions in the cosmos, hurl matter at 99.9% of light speed, but still respect the line. The universe allows spectacle, but it forbids transgression. And yet, within this unforgiving boundary, a question arises. If nothing can move through space-time faster than light, what about space-time itself? The expansion of the universe after the Big Bang suggests that space can stretch faster than light, carrying galaxies apart at rates no particle could achieve. Inflation, the rapid swelling of the early cosmos, outran light with ease. Here lies a subtlety. The speed limit applies to motion within space-time, not to the expansion of space-time itself. This distinction is the crack through which imagination slips, asking whether the very fabric might be manipulated to allow shortcuts. The idea is intoxicating. If space-time can expand to separate galaxies faster than light, could it not also contract or expand locally to carry a starship? If gravity already bends space into orbits and curves light into arcs, could the same curvature be engineered into a bubble of faster-than-light motion that does not violate relativity's rules? This speculation led to Miguel Alcubierre's famous solution in the 1990s, a mathematical construction showing that a warp bubble was permitted by Einstein's own equations. The ship within would never exceed light speed locally, but space itself would do the work, contracting ahead, expanding behind, carrying it faster than light relative to distant stars. Here the contest becomes real. Gravity, with its relentless enforcement of the speed limit, is challenged by warp theory, which proposes to turn the very rules against themselves. It does not break relativity, it bends it. It exploits the distinction between moving through space-time and moving space-time itself. The cosmic speed limit remains inviolate, yet the dream of outrunning light flickers anew, not as fantasy, but as mathematical possibility. The cosmic speed limit, then, is both law and inspiration. It is the reason faster-than-light motion is impossible, and the reason warp theory is compelling. Without the boundary, there would be no need for cleverness. With it, imagination seeks loopholes. As this chapter ends, the rules are clear. Nothing with mass can ever reach light speed. Gravity itself respects the line. Causality depends on it. But the next chapter dares to ask, can warp speed find a path through the geometry of Einstein's own theory, a way to race gravity at its own game? For generations, warp speed was nothing more than a story. It was born in the scripts of television and the pages of novels, a tool for storytellers who refused to let physics slow their adventures. In Star Trek, starships leapt across the galaxy in hours, carried not by rockets, but by the bending of space itself. Writers spoke of warp drives, warp factors, and warp bubbles as though they were real, embedding them in the language of exploration until audiences half believed they might one day exist. These stories were never bound by equations. They were bound only by imagination, and yet imagination has power. It plants seeds in minds willing to ask whether fiction hides truth. The leap from story to science came in 1994, when Mexican physicist Miguel Alcubierre proposed a solution to Einstein's equations of general relativity that mimicked the warp drive of science fiction. He asked a daring question. If relativity prevents any object from moving faster than light, could space-time itself be reshaped to carry a ship faster than light, without the ship ever locally exceeding the limit? His answer was astonishing. Using the mathematics of general relativity, he described a bubble of space-time that contracted ahead of the ship and expanded behind it. Inside the bubble, the ship would float, never accelerating past light speed. Outside, the bubble itself could move faster than light, relative to distant observers. This was not fantasy. It was a legitimate solution within the framework of Einstein's theory. For the first time, warp speed was no longer only fiction. It was a concept that could be written on chalkboards and explored through equations. The Starship Enterprise had slipped from television into physics journals. Alcubierre's drive showed that relativity's own rules allowed loopholes, not by breaking them, but by bending them. Light speed remained unchallenged locally, yet the bubble allowed apparent faster-than-light travel on a cosmic scale. The mechanism was elegant. Imagine space as a rubber sheet. Place a starship on the sheet, and the rules forbid it from sliding faster than a certain limit. But if the sheet itself is stretched behind the ship and compressed in front, the ship rides the wave, moving farther across the sheet than it could by sliding alone. The ship itself feels no acceleration, experiences no g-forces, and never violates the laws of relativity. The motion is in the fabric, not the craft. It is space-time that does the traveling, carrying the ship like a surfer on a cosmic wave. The idea electrified physicists and science fiction fans alike. At last, here was a bridge between dream and science, a way to imagine interstellar travel without discarding Einstein. But the equations carried shadows. Alcubierre's warp bubble required exotic forms of matter with negative energy density, something no experiment had ever confirmed. Worse, early calculations showed that the energy required to create a bubble large enough to carry even a small ship was greater than the total energy of the observable universe. The drive was mathematically possible, but physically absurd. Yet the door had opened. Once the idea existed, refinements followed. Physicists began exploring whether the energy requirements could be reduced, whether negative energy could be produced in tiny amounts, whether quantum fields might supply the exotic matter. Each step brought warp speed closer to plausibility, though still out of reach. The equations showed what was allowed. The challenge became whether reality could supply the ingredients. Warp speed had crossed a boundary of its own. No longer confined to fiction, it now lived in speculation tested against mathematics. It remained impossible, but not forbidden. For humanity, this was enough. A dream once dismissed outright had been admitted into the conversation of science. The rules of relativity were still intact, but within them lay the possibility of bending space to carry us beyond light. The ultimate race had gained a new contender, one with equations in its corner. The Alcubierre drive was more than a clever metaphor. It was a precise mathematical construction. In his solution, space-time itself is reshaped into a bubble that slides through the universe. Within this bubble, a ship sits still, untouched by acceleration. The bubble contracts the fabric of space ahead while stretching it behind, carrying the ship along like a raft on a moving river. To outside observers, the bubble can move faster than light. To those inside, the journey feels effortless. No G-forces, no need for engines pushing against the void, only the quiet hum of geometry in motion. This design avoids the trap of relativity. Locally, the ship never exceeds light speed. No particle within the bubble outruns photons in its vicinity. The speed limit is preserved in every neighborhood of space-time. Yet globally, the bubble can cross distances faster than light could travel them. In this way, Alcubierre showed that Einstein's own equations contain room for apparent faster-than-light motion, not by breaking laws, but by bending the stage itself. It was not cheating the system. It was playing by its deepest rules. But the mathematics came with a catch so severe, it nearly crushed the idea at birth. To create such a warp bubble required exotic matter with negative energy density, a kind of fuel utterly unlike anything known in nature. Ordinary matter has positive energy, whether in stars, planets, or human bodies. Negative energy would be its opposite, a substance that does not simply lack energy, but possesses less than zero. It would gravitationally repel rather than attract, curving space-time outward instead of inward. This was not a minor detail. The very structure of the warp bubble depended on it. Without negative energy, the bubble could not form. Where could such energy come from? Quantum theory provides hints. The Casimir effect, observed in laboratory experiments, shows that the vacuum of space is not empty, but teeming with fluctuations. Two plates placed close together in a vacuum feel an attractive force, because the quantum fluctuations between them are suppressed compared to those outside. This effect is sometimes described as a manifestation of negative energy density. If such fluctuations could be harnessed, perhaps they could provide the exotic matter needed for a warp bubble. Yet the amounts produced in experiments are minuscule, far too small to power even a grain of dust, let alone a starship. The energy requirements themselves were staggering. Early calculations showed that to create a bubble large enough for a modest craft would demand more energy than contained in the entire observable universe. This was not merely impractical, it was impossible. No civilization, no matter how advanced, could command such power. The dream seemed crushed under the weight of numbers. Warp speed might be allowed by mathematics, but it appeared forbidden by reality. Still, physicists refused to abandon the idea. Over the years, refinements to Alcubierre's model suggested ways to reduce the energy demands. By altering the shape of the bubble or considering different space-time geometries, estimates dropped from universal scales to planetary ones, and in some speculative versions, even to masses comparable to Jupiter. Still far beyond human capacity, but orders of magnitude closer than infinity. The challenge became less about dismissing warp speed outright, and more about asking whether the exotic matter it required could exist in usable amounts. The Alcubierre drive thus stands at a strange crossroads. It is mathematically sound, but physically tenuous. It exists in equations, but not in laboratories. It does not violate relativity, but it demands ingredients the universe may never provide. And yet, the very fact that it exists in theory changes the game. Warp speed is no longer only the domain of imagination. It is a question for physics itself, a challenge thrown at gravity's authority, asking whether space-time can be manipulated in ways that nature has so far kept hidden. The concept remains speculative, but speculation itself is powerful. It pushes boundaries, forces questions, and demands deeper understanding. Warp speed may never leave the realm of theory, but by existing within the framework of Einstein's equations, it shows that even the cosmic speed limit may not be as absolute as once believed. The race between gravity and warp has begun, not in starships, but in chalk dust and quantum fields. To imagine a warp bubble is to imagine a journey unlike any in human history. Inside the bubble, the crew of a ship would feel nothing unusual. There would be no shudder of acceleration, no crushing G-forces, no sensation of motion at all. Time would flow normally within the cabin, clocks ticking at their familiar rhythm. The ship would not roar through space. Instead, space itself would be carried past the ship. Stars would appear to shift, not because the vessel was moving through them, but because the bubble was sliding across space-time like a ripple in water. To those aboard, the trip would feel almost tranquil, yet to an outside observer, the ship would be racing across light years in mere moments. But the bubble is not gentle to its surroundings. The mathematics suggests that energy builds at its leading edge, accumulating into a wave of intense radiation. Any matter in front of the bubble could be blasted with destructive force when the drive disengages. Behind the ship, the expansion of space leaves distortions that may fling particles into chaos. To observers outside, the warp bubble would not look like a sleek vessel slipping past the stars. It would be a distortion, a region of warped light and bent geometry, its edges shimmering with gravitational stress. To see such a thing would be to glimpse the raw fabric of space-time torn and reshaped in motion. Practical challenges arise immediately. How would such a bubble be created in the first place? The equations show what is possible, but say nothing of engineering. Where does the negative energy come from? And how is it shaped into the right configuration? How would the bubble be stabilized, preventing collapse or runaway expansion? How would a crew steer it or shut it down safely at a destination? These are questions with no answers yet. The Alcubierre drive is elegant in theory, but silent on mechanics. Between mathematics and reality lies a gulf as wide as the distance between stars. Even so, the concept is tantalizing. For centuries, faster-than-light travel had been dismissed as fantasy. Now, at least in equations, it has been admitted as a possibility. Not a likelihood, not a practicality, but a possibility. That alone reshapes the conversation. If the universe allows such solutions, then perhaps the laws of physics are not as constraining as they appear. Perhaps what seems impossible today may, in some unimaginable future, become a feat of engineering. History has taught us to be cautious, but also to be bold. Heavier than air flight was once absurd. Splitting the atom was once inconceivable. Space travel was once a dream. Each became real through persistence and discovery. Warp speed may yet join them, or remain forever a shimmering mirage in mathematics. As this chapter closes, we leave warp speed in a strange position. It is no longer only fiction, but neither is it fact. It stands between the two, a solution etched in relativity's equations, but chained to requirements we cannot meet. It promises journeys beyond imagination, yet demands fuels beyond reality. The race between gravity and warp is no longer only philosophical. It has become scientific, and science will decide whether the dream survives. Next, we turn to the cost of the dream. If warp is possible in principle, what does it demand in practice? The answer is staggering. Energy requirements beyond reason, negative matter that may not exist, and barriers that dwarf even our boldest achievements. Warp speed may live in equations, but reality has the final word. The next chapter reveals just how steep the price would be to race against gravity. The Alcubierre drive startled physicists, not because it broke relativity, but because it obeyed it. Within Einstein's equations lay the blueprint for a warp bubble, a configuration of space-time that allowed apparent faster-than-light travel without violating the speed limit locally. It was a loophole hiding in plain sight. But as with all loopholes, the fine print proved merciless. The mathematics that permitted the bubble also demanded a price so immense that the dream collapsed under its own weight. The first reality check came in the form of energy. Early calculations estimated that to create a bubble large enough to carry even a modest craft would require energy greater than the mass energy of the observable universe. Not a star, not a galaxy, but all galaxies combined. The number was so vast that it defied comprehension. Even if every atom of matter in the cosmos were converted to energy by Einstein's famous equation E equals mc squared, it would not suffice. The warp bubble, though mathematically allowed, demanded a treasury of energy that reality could never provide. It was as though nature had left the door open but locked it behind a wall of impossibility. To understand why, we must look closer at what a warp bubble requires. Contracting space ahead and expanding space behind is not like inflating a balloon with air. It means altering the curvature of space-time itself, an act that demands enormous amounts of energy. In general relativity, energy is the currency that bends geometry. Ordinary matter bends it inward, creating the familiar attraction we call gravity. To push geometry outward, to create the repulsive expansion required at the rear of the bubble, demands negative energy density. This is not just exotic, it is alien to all known physics. Negative energy is a peculiar concept. It is not the same as having less energy than zero in the usual sense, like a bank account overdrawn. It is a state where the very vacuum of space contains less energy than nothing at all, creating a repulsive gravitational effect. Quantum theory hints at such states. In the Casimir effect, for instance, two closely spaced plates in a vacuum feel an attractive force because quantum fluctuations between them are restricted, leaving a region of suppressed energy density. Some physicists interpret this as a glimpse of negative energy, but these effects are vanishingly small, detectable only in careful laboratory setups, and utterly insufficient for the titanic needs of a warp bubble. The problem is not only the quantity of energy, but its distribution. The Alcubierre solution requires a shell of negative energy surrounding the bubble, balanced against regions of positive energy. The shape must be precise, or the bubble collapses. The energy must be contained, or it tears space-time apart uncontrollably. Even if negative energy could be conjured, shaping it into the required configuration is beyond anything our physics or technology currently permits. It is not merely an engineering problem. It is a fundamental barrier, a mismatch between what the equations describe and what reality seems willing to supply. As these realities sank in, physicists recalculated, hoping refinements might soften the blow. Adjustments to the bubble geometry reduced the energy demands by many orders of magnitude. Instead of requiring the energy of the universe, some models suggested requirements equivalent to a star, then a planet, and in the most optimistic cases, the mass energy of Jupiter. This was progress, but it was progress measured against impossibility. The step from infinity to a planet's worth of energy is immense, yet still utterly beyond human reach. No civilization could harness such power without technology indistinguishable from magic. This is the paradox of warp speed. It is not forbidden by relativity, yet it is imprisoned by reality. The mathematics shows the door is open, but the price to walk through is astronomical. The challenge is no longer whether warp speed is possible in principle, but whether it is possible in practice. And practice so far is merciless. The dream stands against numbers that dwarf imagination. The race between gravity and warp is not only about rules, it is about costs. Gravity demands nothing but patience. Warp demands everything we do not have. Physicists are not easily deterred by impossible numbers. The history of science is filled with barriers once thought insurmountable, only to yield under closer scrutiny. When Alcubierre's drive was first examined, the energy requirement seemed so absurd, greater than the mass energy of the observable universe, that many dismissed it outright. But others pressed on, asking whether the mathematics could be reworked, whether the bubble's structure could be reshaped to ease its appetite for energy. The result was a series of refinements that chipped away at the demands, reducing them by orders of magnitude. One approach focused on the geometry of the bubble itself. The original model assumed a perfectly symmetrical shape, simple in equations but extravagant in cost. By adjusting the profile of the bubble, making it thinner in some regions and thicker in others, researchers found that the energy requirement could be reduced drastically. Instead of the energy of the cosmos, later estimates suggested the energy equivalent of a star, then a planet, and in the most optimistic models, something on the scale of a massive spacecraft. This was still impossibly far from human capability, but the leap from universal to planetary to local at least showed progress. The dream was no longer infinitely expensive. It was merely fantastically so. Yet the deeper obstacle was never only the amount of energy, it was the type. The warp bubble does not simply demand energy in general, it demands negative energy density, something no known form of matter or radiation provides. Ordinary energy bends space-time inward. Negative energy bends it outward, repelling rather than attracting. This property is essential to the Alcubierre design, which requires expansion of space behind the bubble. Without negative energy, the mechanism fails. And negative energy is not something humanity can generate on demand. Quantum field theory provides glimpses of negative energy in phenomena like the Casimir effect, where closely spaced metal plates experience an attractive force due to the suppression of vacuum fluctuations between them. In a sense, this represents a region of reduced energy density compared to the surrounding vacuum, which can be interpreted as negative energy. But the scale of the effect is microscopic, detectable only with sensitive instruments and completely negligible compared to what a warp bubble would require. Scaling such an effect up by many orders of magnitude is beyond any plausible technology. Some have speculated that dark energy, the mysterious force accelerating the expansion of the universe, might be related to the kind of negative energy required. But dark energy is uniform, filling all of space evenly, and cannot be localized into the structured shell the Alcubierre drive demands. Harnessing it, if it is even possible, would be like trying to sculpt a hurricane into the shape of a thread. It is not only impractical, but conceptually mismatched. Even if negative energy could somehow be produced or harvested, the problem of stability remains. A warp bubble is not a static object. It would need to be created, sustained, and guided. The equations do not explain how to switch it on, how to prevent it from collapsing, or how to shut it down safely at a destination. Without precise control, the bubble could tear itself apart, destroying the ship, and perhaps anything nearby. Stability is not a minor technicality. It is a fundamental requirement for survival, and one we have no clear path toward meeting. The reality check grows harsher when we consider engineering. Energy on the scale of Jupiter's mass would need to be concentrated into a configuration of exotic matter with properties we cannot produce, shaped into a precise shell and sustained over interstellar distances. This is not simply beyond our present technology, it is beyond anything that can be imagined with current physics. The gap is not a century or a millennium. It may be unbridgeable, and yet the idea persists. Even if the obstacles are immense, the very fact that warp speed exists as a solution in relativity means it cannot be dismissed entirely. It remains possible in principle, even if impractical in practice. The race between gravity and warp is therefore more nuanced than victory and defeat. Gravity wins today, unchallenged in reality. Warp survives as a hope, a mathematical possibility clinging to the edge of plausibility. The contest is ongoing, not on starships or battlefields, but in equations, experiments, and the stubborn refusal of imagination to yield. The deeper we examine the Alcubierre drive, the clearer its paradox becomes. It is permitted by the equations of general relativity, yet obstructed by the realities of physics. On paper, warp bubbles glide serenely through space-time, carrying ships across light years in the blink of an eye. In practice, they demand energy so vast and materials so exotic that the dream collapses under its own conditions. It is as though the universe itself teases us with possibility, offering the blueprint for faster-than-light travel, but hiding the tools behind walls we cannot breach. The sheer scale of the problem is humbling. Gravity bends space effortlessly. A star curves the paths of planets without struggle. A galaxy warps the light of distant objects as naturally as breath. The expansion of the universe stretches space across billions of light years without any intervention at all. In contrast, our imagined warp bubbles require astronomical effort just to mimic what gravity already accomplishes with ease. Nature sculpts space-time as casually as clay, while we, with all our ingenuity, struggle to imagine even the faintest means of reshaping it. This comparison reveals a deeper truth about the race between gravity and warp. Gravity is not only the reigning champion, it is the effortless one. It bends, curves, expands, and contracts space-time without cost, without strain, as a direct consequence of mass and energy. Warp, by contrast, is fragile and demanding. It does not flow naturally from the laws of physics. It exploits a loophole that can only exist under conditions so extreme that reality itself resists them. Warp is possibility at the edge of imagination. Gravity is reality at every scale. And yet, humanity cannot help but cling to the dream. Even if the energy costs are staggering, even if exotic matter remains elusive, the vision of warp speed continues to inspire. It represents more than travel. It represents freedom from limits, defiance of distance, the assertion that the cosmos is not too vast for us to cross. The fact that the dream persists, despite the obstacles, is itself a testament to human stubbornness. For thousands of years, we have faced the impossible and asked, what if? Warp speed is the latest incarnation of that impulse. But reality must be faced. For now, warp exists only in equations, its costs unreachable, its requirements unattainable. Gravity holds the crown of practicality. The stars remain distant, their light crossing gulfs we cannot hope to outrun. If the dream of warp is ever to move closer to reality, it will demand new physics, breakthroughs as profound as relativity itself. Until then, gravity rules not only as the architect of motion, but as the sole master of shortcuts. Yet gravity has its own secrets, its own loopholes hidden in the folds of space-time. Wormholes, theoretical tunnels linking distant regions of space, are as much a product of Einstein's equations as warp bubbles. Like warp, they rely on exotic conditions and immense energies. But unlike warp, they emerge naturally from gravity's mathematics. The next chapter turns to these gravitational shortcuts, exploring how nature itself may already provide the pathways warp aspires to mimic. If warp speed represents humanity's attempt to outwit the universe, wormholes are the universe's own trick. They are not inventions of science fiction, though fiction has embraced them eagerly. They are solutions to Einstein's equations, emerging naturally from the mathematics of general relativity. In theory, a wormhole is a bridge through space-time, a tunnel linking two distant regions. To step through one mouth would be to emerge instantly at the other, no matter how vast the gulf between them. Where warp bubbles carry ships by distorting space, wormholes erase the distance altogether. The concept can be traced to 1935, when Albert Einstein and Nathan Rosen explored the mathematics of general relativity and discovered a structure that seemed to connect 2 points in space-time. Known as the Einstein-Rosen bridge, it was an early wormhole, though one too unstable to remain open. Later, physicists refined the idea, showing that under certain conditions, a traversable wormhole might exist. Unlike the warp drive, which requires us to push space-time into unnatural contortions, wormholes appear as natural consequences of the geometry itself. They are not fantasies pasted onto equations. They are the equations, revealing possibilities hidden in the depths of gravity's laws. The appeal is obvious. If a wormhole could be stabilized and controlled, interstellar distances would vanish. A ship might enter a wormhole near Earth and emerge near Alpha Centauri in moments. Galaxies separated by millions of light years could be linked like neighboring towns. For civilizations dreaming of exploration, wormholes are the ultimate prize. They offer not just faster travel, but instantaneous travel, a cosmic highway bypassing the speed limit altogether. In this vision, gravity does not enforce barriers, it builds bridges. Yet, as always, the fine print of physics intrudes. Wormholes may emerge naturally from relativity, but they are not easily tamed. The Einstein-Rosen bridge collapses too quickly for anything to pass through. The throat pinches shut before light or matter can cross. To keep a wormhole open, exotic conditions are required. Negative energy once again, the same strange ingredient demanded by the Alcubierre drive. Without it, gravity's pull crushes the tunnel, sealing it before it can be used. With it, in principle, the tunnel might be held open, its walls stabilized against collapse. The need for negative energy shows that wormholes and warp drives are cousins. Both exploit relativity's geometry, both promise shortcuts across space, and both demand ingredients the universe seems reluctant to provide. But wormholes differ in one crucial way. They are not artificial manipulations imposed on space-time. They are natural solutions already written into Einstein's equations. If exotic matter exists, even in tiny amounts, wormholes could in theory be coaxed into stability. They may be rare, fleeting, and dangerous, but their existence is less speculative than warp bubbles. In some sense, they are gravity's own attempt at warp. Wormholes capture imagination as powerfully as warp speed. Countless stories envision travelers stepping into shimmering tunnels, emerging across galaxies, or leaping between parallel universes. Unlike warp, these tales rest on a firmer scientific foundation. The equations allow wormholes. They are not forbidden. Their challenge lies not in mathematics, but in reality. Finding or creating one, stabilizing it, and surviving its passage. If warp bubbles represent humanity's ambition, wormholes represent gravity's invitation, tantalizing, treacherous, and perhaps just out of reach. Wormholes, though elegant in equations, are treacherous in practice. The simplest versions collapse before they can be used. Like soap bubbles pinching off as soon as they form, their throats contract under gravity's pull, sealing shut faster than light can cross them. To remain traversable, a wormhole must resist its own collapse. This is where the strange requirement of negative energy enters once again. Without it, the tunnel cannot stay open. With it, the walls might be propped against gravity's relentless grip, holding the throat wide enough for matter and light to pass. Physicists call these traversable wormholes. Unlike the original Einstein-Rosen bridges, which vanish instantly, a traversable wormhole could remain open long enough for a spacecraft to cross. In principle, it would function as a cosmic tunnel, linking distant points of space or even distant times. But in practice, the demands are as daunting as those of warp bubbles. The amount of negative energy required is staggering, and the configuration must be exact. Too little, and the tunnel collapses. Too much, and the geometry becomes unstable, threatening to tear itself apart. Precision is everything, and precision at this scale is far beyond anything we can achieve. Even if the stability problem were solved, wormholes present other hazards. The tidal forces inside a throat could be immense, stretching and compressing anything that enters. Radiation may build at the entrance, flooding travelers with lethal doses. Quantum instabilities could trigger collapse without warning, trapping or destroying whatever lies inside. Unlike warp bubbles, which carry their contents in calm isolation, wormholes expose their travelers to the raw turbulence of curved space-time. Crossing one would not be like stepping through a doorway. It would be like plunging into a storm made of geometry itself. Despite these dangers, wormholes remain alluring because they are not purely speculative. They emerge directly from general relativity, the same framework that has predicted black holes, gravitational waves, and the expansion of the universe, all phenomena once doubted, but now confirmed. If black holes can exist, if space-time can ripple, why not wormholes? They may be unstable, fleeting, or microscopic, but their possibility is not fantasy. It is written in the same equations that describe reality so accurately elsewhere. This raises an intriguing thought. Perhaps wormholes exist naturally in the universe, forming at quantum scales in the foamy structure of space-time. If so, they may be ephemeral, opening and closing too quickly to be useful. But if technology one day finds a way to stabilize or enlarge them, wormholes could become more than curiosities. They could become highways. In this sense, wormholes are gravity's own shortcuts, potential pathways already embedded in space-time's fabric, waiting for someone to find the right conditions to exploit them. The parallel with warp speed is striking. Both require exotic energy, both promise faster than light travel without violating relativity, and both hover at the boundary between mathematics and possibility. The difference is that warp bubbles must be engineered deliberately, while wormholes may already exist in some hidden form, waiting to be discovered. Warp represents human ambition, bending the universe. Wormholes represent the universe bending itself, offering a chance, however slim, that the cosmos has already built the bridges we seek. The idea is intoxicating, but sobering too. Just as warp drives demand impossible energy, wormholes demand impossible stability. Gravity opens doors only to slam them shut. The shortcuts exist in theory, but the price of using them remains as steep as ever. If the universe allows travel through its hidden tunnels, it does not allow it cheaply. When we compare wormholes to warp drives, we find a striking symmetry. Both are born from Einstein's theory of relativity, not from outside it. Both promise to carry travelers faster than light without breaking the sacred speed limit. Both rely on bending space-time itself, not pushing through it. And both demand exotic matter or negative energy that has never been found in usable form. In their similarities, they reveal a profound truth. The universe allows shortcuts in principle, but not without conditions so extreme that they may forever remain beyond reach. Yet their differences matter too. Warp drives are inventions of human imagination, mathematical constructs designed to mimic the fantasies of fiction. They are artificial in conception, requiring civilizations to engineer space-time into shapes never seen in nature. Wormholes, by contrast, arise spontaneously from relativity's equations. They are not inventions, but possibilities, waiting in the mathematics like hidden passages in a labyrinth. Warp is ambition. Wormholes are discovery. Warp is an attempt to cheat the rules. Wormholes are the rules, whispering that shortcuts may already exist. If either could be made real, the implications would be staggering. Warp would allow ships to cross galaxies as easily as oceans, carrying civilizations outward into the stars. Wormholes would do the same, but with an even more radical twist. Not travel, but connection. A wormhole is not a journey through space. It is a bridge collapsing distance entirely, turning vast gulfs into single steps. The difference is profound. Warp respects distance but cheats time. Wormholes erase distance altogether. In a universe shaped by gravity, they are the most audacious of gifts. But gifts in physics are rarely free. The obstacles to both are colossal, and the similarities in their demands suggest a deeper lesson. The need for negative energy may not be coincidence. It may be a signal that faster-than-light shortcuts, whether warp bubbles or wormholes, all live on the same knife edge of physics, allowed by equations, but punished by reality. Nature seems willing to grant the idea, but unwilling to grant the means. The rules are consistent, the door half open, the threshold guarded by requirements that no known process can meet. This does not end the story. Humanity has faced impossibilities before, only to turn them into achievements. What once seemed fantasy, flight, nuclear power, space travel, has become reality. Wormholes and warp drives may yet join them, if new physics or technologies reveal ways to tame the impossible. For now, they remain as symbols, reminders that even gravity, the great enforcer of limits, carries within its equations hints of rebellion. It is as if the universe itself acknowledges the dream, offering glimpses of what could be, even as it denies the tools to make it real. As we leave wormholes, we return to the central contest. Gravity bends space-time with effortless authority, shaping galaxies and horizons. Warp tries to mimic it, demanding energy beyond imagination. Wormholes represent gravity's own version of the same idea, natural tunnels hidden in its geometry. The question is no longer whether shortcuts exist in theory. They do. The question is whether they can ever be made real. The stage is set for the next act, not just a race of speed, but a test of physics itself. For when warp confronts relativity directly, the battle is no longer about distance. It is about the very nature of reality. Warp drives, wormholes, and faster-than-light dreams all exist within the mathematics of relativity. yet they stand in tension with its deepest principles. General relativity is not merely a set of equations. It is the architecture of causality, the blueprint that ensures events unfold in consistent order. To propose a warp bubble or a traversable wormhole is to test the very structure that relativity defends. The question is not simply whether these constructs can exist, but whether their existence would fracture the logic of the universe itself. At the heart of the issue lies causality. Relativity enforces a strict rule: cause must precede effect. Signals cannot outrun light because doing so would allow an effect to occur before its cause in some reference frames. This is not a minor oddity. It is a violation of logic, a collapse of order. Faster than light travel risks opening the door to paradoxes, events that defy consistency. A message sent faster than light might arrive before it was transmitted. A traveler might return to their own past. The result is not merely confusion, but contradiction. Histories that cannot coexist, outcomes that destroy themselves. Physicist Stephen Hawking argued that nature abhors such violations. He proposed the chronology protection conjecture, a principle suggesting that the laws of physics prevent time paradoxes from arising. According to this idea, wormholes or warp bubbles that could enable backward time travel would destabilize, collapse, or become flooded with radiation before paradoxes could occur. In this view, relativity contains within it a defense mechanism, a kind of cosmic firewall against causality's breakdown. The universe protects its timeline by refusing to allow shortcuts that would fracture it. But the matter is not settled. Mathematical models of warp bubbles and wormholes do suggest paths that could allow closed time-like curves, loops in space-time where a traveler might return to their own past. These are not speculative fantasies. They are direct consequences of manipulating space-time geometry in certain ways. If such structures could exist, time travel would not be optional. It would be unavoidable. The same mechanisms that allow faster than light travel can, in theory, fold space-time into paradoxes. The race between gravity and warp thus becomes a deeper battle, not speed against speed, but consistency against contradiction. This tension is why physicists treat warp drives with both fascination and skepticism. On the one hand, the equations permit them. On the other, the consequences threaten to unravel the very fabric relativity is built to preserve. The paradoxes are not bugs in the model. They are features, emerging naturally from the manipulation of space-time. To accept warp is to accept that causality itself may bend or break. And if causality breaks, what becomes of physics? To imagine a warp drive in operation is to confront these paradoxes directly. A ship could, in principle, leap across light years in moments, but in some frames of reference, that leap would resemble a journey backward in time. Communication between such ships could produce contradictory timelines, messages arriving before they were sent. The consistency of events, the bedrock of science, would fracture. The laws that govern reality might still hold, but the order they protect would dissolve. This is the edge on which warp theory balances, between the promise of speed and the threat of paradox. The possibility of paradox is not just a philosophical concern. It emerges directly from the mathematics of relativity when space-time is bent into extreme geometries. A closed time-like curve, a path through space-time that loops back onto itself, is one such geometry. In ordinary conditions, such paths cannot exist. The curvature produced by stars, planets, or black holes does not allow them. But in the presence of a traversable wormhole or a carefully configured warp bubble, relativity permits them to arise. Suddenly, a traveler could follow a path that delivers them back to the very moment they began, carrying memories and actions that could undo the conditions of their departure. This is the seed of paradox. Imagine sending a message back to yourself with instructions that prevent you from sending the message in the first place. Or imagine traveling back in time to stop an event whose prevention eliminates the reason you traveled at all. These contradictions are not puzzles to be solved. They are inconsistencies that cannot exist within a logical framework. If physics allows them, it ceases to be a consistent description of reality. This is why paradoxes are treated not as curiosities, but as threats to the very coherence of the universe. Stephen Hawking's chronology protection conjecture was a response to this threat. He argued that the universe contains built-in mechanisms to prevent such scenarios. Wormholes that could allow backward time travel, he suggested, would become unstable under quantum effects. Radiation would flood the throat, collapsing it before paradoxes could occur. Warp bubbles that could create closed time-like curves would face similar instabilities, tearing apart under the very conditions needed to sustain them. In this view, relativity defends itself, ensuring that while equations may hint at paradoxes, reality forbids them. Evidence for this protection lies in the universe itself. Nowhere in nature have we observed time loops, backward causality, or faster-than-light signals. Every test of relativity affirms its consistency. Gravitational waves, pulsars, and black holes all behave according to rules that preserve causality. If loopholes exist, they are tightly sealed by barriers of energy, stability, or quantum effects. It may be that relativity tolerates the mathematics of paradox only to close the door in practice, ensuring the universe remains safe from contradiction. Yet not all physicists are convinced. Some argue that paradoxes may be avoided not by preventing time travel, but by changing its meaning. In one interpretation, events on closed time-like curves are self-consistent. A traveler who journeys to the past cannot change it, but only fulfill it. Their actions become part of history, woven into the timeline in a way that avoids contradiction. This idea, known as the Novikov self-consistency principle, allows time travel without paradox at the cost of free will. The past cannot be changed because it is already fixed, even if by your own hand. Such notions stretch the boundaries of science into philosophy. Do the laws of physics allow freedom, or do they enforce consistency at all costs? If warp drives or wormholes could exist, would they grant us true, faster-than-light travel, or would they bind us in loops where our choices are already written? These are not questions that equations alone can answer. They cut to the heart of what it means for the universe to have order. For now, relativity has never failed in its predictions. Every observation affirms that causality holds firm, that no signal outruns light, that no paradox arises. But the theoretical existence of warp bubbles and wormholes keeps the tension alive. They remind us that the universe's laws may have loopholes, and that those loopholes may come with costs we are not prepared to pay. The clash between warp and relativity is not about speed alone. It is about the survival of order itself. Relativity sets the cosmic stage where events unfold in sequence, bound by the speed of light. Warp drives and wormholes tempt us with ways to skirt that sequence, to bend time and space into shortcuts. The mathematics permits them, but the consequences reach beyond engineering. They threaten the logic that makes reality intelligible. To embrace warp without caution is to risk unraveling causality, the thread that ties every effect to its cause. And yet, to dismiss warp outright would be premature. The Alcubierre drive does not technically violate relativity. Locally, no object in the bubble moves faster than light. The geometry of space-time itself is what carries the ship. In this sense, warp is a loophole, not a violation. It obeys the rules while reshaping the field on which they are played. Whether such a loophole can exist in practice is another matter, but in theory, relativity tolerates it. The paradoxes arise not because warp defies relativity, but because it extends its geometry into extreme configurations where causality bends under its own weight. Here lies the ambiguity. Relativity allows warp in principle, but perhaps not in reality. Quantum effects may destabilize it. Exotic matter may never exist. Chronology protection may intervene. If so, relativity remains unbroken, its authority intact. But if warp is possible, even as a fragile loophole, then relativity is not as final as it appears. It becomes a framework that tolerates exceptions, rare and extreme, yet real. The difference is profound. Relativity would no longer be absolute law, but the canvas for deeper physics still to come. This is why warp fascinates physicists as much as storytellers. It challenges not only our engineering, but our understanding of reality. If it exists, causality may need to be reinterpreted, paradoxes avoided by principles we do not yet grasp. If it does not exist, its mathematical possibility still pushes us to probe the limits of relativity, to ask whether the universe hides deeper layers of law. Warp, even as speculation, is a mirror reflecting the fragility of our assumptions. For now, gravity holds the advantage. It curves space-time naturally, bending light and shaping time without paradox or instability. Warp remains theoretical, dependent on conditions nature may forbid. The race is not won by speed, but by consistency, and relativity's track record is flawless. Warp exists in the margins of equations, gravity in the heart of reality. But the contest is not over. If warp bubbles or wormholes could ever be created, they would not remain hidden. They would leave signatures, distortions of light, accumulations of radiation, shifts in geometry visible across the cosmos. The next chapter asks what such phenomena might look like, not in theory, but in observation. If warp drives or wormholes exist, even in some corner of the universe, how would we see them? What would their presence reveal, and what dangers would they unleash? If warp drives or wormholes were ever realized, they would not pass through the universe unnoticed. The bending of space-time is not invisible magic. It leaves fingerprints, distortions written into the light, radiation, and geometry around it. To imagine faster than light travel is not only to imagine journeys through the stars, but also to imagine what the rest of the cosmos would see when such journeys unfold. The consequences would not be subtle, they would be spectacular. Consider a starship inside a warp bubble. From within, the crew would feel calm, time flowing normally, stars sliding silently across the viewport as the bubble carried them forward. But to an outside observer, the scene would be anything but ordinary. Light passing near the bubble would bend and distort, just as it bends around massive stars or galaxies. The edges of the bubble would shimmer with gravitational lensing, creating arcs, streaks, or halos of displaced starlight. The ship itself might vanish from view, hidden behind distortions of its own making, a ghost wrapped in ripples of warped geometry. Colors would shift as well, just as ordinary motion produces the Doppler effect, with waves compressed in front and stretched behind. Warp motion would exaggerate this to extremes. Ahead of the bubble, starlight would blue shift, compressed into higher energies. Behind, it would redshift, stretched into longer wavelengths. To a distant observer, a warp bubble could appear as a glowing sphere, its front edge blazing with intense radiation, its rear fading into deep crimson. The ship inside might be invisible, but the bubble itself would announce its presence in vivid hues. The danger of this compression is more than visual. High-energy particles in interstellar space would pile up at the front of the bubble, compressed like snow against a plow. Radiation would accumulate, potentially reaching levels so extreme that when the bubble collapsed, it would release a destructive burst. For a ship, this could mean catastrophic hazards when arriving at its destination. For any world near its exit point, it could mean devastation. The very geometry that carries the ship could also weaponize the cosmos against it. Wormholes would produce their own spectacles. Light skimming the mouth of a wormhole would split and distort, creating rings and arcs much like gravitational lensing, but with even stranger signatures. One might see duplicate images of stars, echoes of light from regions beyond normal reach. Entering a wormhole could resemble plunging into a sphere of distorted starlight. The universe bent into impossible geometries at the edge of visibility. If such objects exist in nature, they may already reveal themselves in astronomical surveys, hidden among the curiosities of distorted galaxies and unusual lensing events. These observational consequences matter because they are testable. If warp bubbles or wormholes could exist, they would alter the flow of light and matter around them in predictable ways. Astronomers could, in principle, detect them not by chasing ships, but by studying distortions in the sky. The absence of such evidence so far suggests that, if shortcuts exist, they are not common. Yet the possibility remains that one day we might stumble upon a signature too strange to dismiss, a cosmic anomaly that whispers of warp or wormholes at play. The consequences extend beyond visibility. A ship at warp would not only bend light, but also drag space-time with it. Gravitational waves could ripple outward as the bubble accelerates or collapses, detectable by instruments like LIGO and Virgo. The pattern of such waves would differ from those of black hole mergers or neutron-star collisions, offering a unique signature. A civilization with warp technology might therefore announce its presence unintentionally, broadcasting its voyages across the cosmos through ripples in space-time. Observation is the final test of theory. Mathematics may permit warp bubbles and wormholes, but if they exist, they must leave marks in the sky. Those marks would be unmistakable. Distortions of light, floods of radiation, ripples in space-time. To dream of faster-than-light travel is to dream also of consequences, some wondrous, some catastrophic. Warp and wormholes would not hide in silence. They would shout their presence across the universe. Gravitational lensing offers a natural guide to what warp distortions might resemble. When light passes near a massive galaxy cluster, its path bends, creating arcs and rings that astronomers call Einstein rings. These distortions reveal the hidden presence of dark matter and the invisible scaffolding of the cosmos. A warp bubble would create similar effects, but far stranger. Instead of a smooth lens shaped by gravity's pull, the bubble would act as a moving distortion, bending light asymmetrically as it slides through space. To a distant observer, stars might flicker or split into ghostly doubles as the bubble passed, the sky warping like heat haze on a desert horizon. For the crew inside the bubble, the view would be equally strange. Ahead, the sky would compress into a narrow cone of blue-shifted starlight, the stars crowding together into a brilliant spear of light. Behind, the sky would stretch into darkness, stars reddened and receding. It would be as if the universe itself were tilting, pouring forward into the ship's path. The ship would not feel acceleration, but the visual distortion would be profound, a reminder that motion at warp is unlike any journey humans have ever known. But these distortions carry danger as well as beauty. The compression of radiation at the bubble's front is not merely a visual shift. It concentrates energy. Interstellar particles, normally harmless at slower speeds, would accumulate into a deadly wall of high-energy radiation. When the bubble collapses, this radiation could be released in a destructive burst, frying electronics, sterilizing planets, or even devastating entire regions of space. Warp may solve the problem of distance, but it introduces hazards that make the destination perilous. Wormholes present their own dangers. A traversable wormhole would bend light into spectacular arcs, but its throat would also be a zone of extreme stress. Matter entering could be stretched or compressed by tidal forces, torn apart before reaching the far side. Even if negative energy stabilized the throat, instabilities could still arise. Quantum fluctuations might trigger collapse, crushing the traveler mid-passage. Radiation trapped inside could bounce endlessly, building to levels that incinerate anything daring to cross. Where warp bubbles risk destruction at their edges, wormholes risk annihilation at their core. For civilizations advanced enough to attempt these shortcuts, the dangers might be manageable. Exotic shielding, precise control of space-time geometry, or manipulation of quantum fields might tame the hazards. But for us, they are reminders of how unforgiving the universe is. Faster than light travel is not merely an engineering challenge. It is a confrontation with the raw geometry of reality, a battle against distortions and instabilities that make space itself hostile. Yet these very dangers provide opportunities for detection. A warp bubble, releasing radiation at its front would shine like a beacon, visible to sensitive telescopes. A wormhole scattering light into strange arcs would betray its presence across the sky. Gravitational waves produced by their motion or collapse would ripple outward, detectable by instruments tuned to the whispers of space-time. If such phenomena exist, we may one day find them not by searching for ships, but by studying anomalies in the cosmic background. The lesson is clear: warp and wormholes cannot hide. Their distortions are their signatures, and those signatures may one day serve as evidence of civilizations that have bent the rules of physics. But even if none are found, the predictions sharpen our understanding of what such shortcuts would cost. Beauty and danger are inseparable at this scale. The universe offers no easy passage, only pathways etched in light, gravity, and peril. If warp bubbles and wormholes were real, their presence would transform the universe into a theater of both wonder and danger. They would be more than tools of travel. They would be engines of creation and destruction, capable of reshaping environments, bending light into breathtaking illusions, and unleashing energies on a scale beyond comprehension. The consequences would not be confined to the ships that use them. They would ripple outward, altering entire regions of space, announcing themselves with signatures no civilization could ignore. The destructive side is easiest to imagine. A warp bubble, by compressing radiation at its leading edge, could unleash devastation when it collapses. The release might resemble a burst of gamma rays, the most violent explosions known in the cosmos, only directed and localized. A single voyage might sterilize worlds or incinerate any unshielded structures near its endpoint. Wormholes could be equally dangerous. Their throats, unstable and volatile, could collapse violently, releasing energy that scars space-time and floods nearby regions with radiation. Faster than light travel would not be gentle. It would be perilous, a technology as threatening as it is liberating. Yet creation is possible too. The bending of space-time can focus light, magnify distant galaxies, or reveal otherwise hidden regions of the cosmos. A wormhole stabilized between 2 points could serve not only as a bridge for travelers, but also as a telescope, offering views across the universe in ways no ordinary instrument could. A warp bubble might manipulate light in ways that allow unprecedented communication, bending signals around obstacles, or transmitting information across vast gulfs. The same phenomena that endanger also empower, giving civilizations that master them unmatched influence over space and time. The observational consequences therefore cut both ways. They warn us of the hazards of meddling with space-time, but they also hint at the power such mastery would bring. Any civilization capable of controlling warp or wormholes would wield forces rivaling stars. Their presence in the cosmos would be unmistakable, their journeys painting the sky with distortions and ripples. Perhaps one day we will recognize such signs, not as natural phenomena, but as the footprints of explorers who have raced gravity and found a way to win. For now, the sky remains silent. We see lensing by galaxies, but no distortions that suggest wormholes. We detect gravitational waves from black hole collisions, but none from warp bubbles. The absence of evidence does not prove impossibility. It only reminds us that, so far, gravity rules alone. The observational consequences of warp and wormholes remain predictions, not discoveries. They live in theory, awaiting either confirmation or dismissal by the universe itself. And so, the contest continues. Gravity demonstrates its authority everywhere we look, bending light, curving time, and shaping galaxies with ease. Warp and wormholes, though mathematically permitted, exist only as possibilities. Which will prevail? The next chapter turns to the heart of the question. Who wins the battle? Gravity with its proven dominance, or warp with its daring loophole? Every contest demands a victor, but the race between gravity and warp is unlike any other. Gravity is not a competitor we invented. It is the foundation of reality itself, shaping every orbit, every star, every galaxy. Warp is a creation of imagination and mathematics, a loophole carved from the very equations gravity obeys. To ask who wins is to ask whether the universe prefers the certainty of what is or the possibility of what could be. Gravity's claim to victory is overwhelming. It is universal, unquestioned, and ever-present, from the smallest pebble falling to Earth to the most massive black hole swallowing stars. Gravity rules without exception. Its power requires no exotic matter, no impossible energy, no speculative engineering. It bends space-time naturally, curving light and slowing time with the effortless certainty of law. Gravity is not a dream. It is reality, tested and proven in every corner of the cosmos. In the contest for practical dominance, gravity has already won. Warp's claim is different. It is not proven, but permitted, not observed, but possible. Its existence is mathematical, a solution etched into Einstein's general relativity, whispering that faster than light travel may not be impossible after all. Warp offers hope against the tyranny of distance, a vision of journeys across galaxies that gravity alone cannot grant. But hope is not proof, and possibility is not reality. Warp survives only as speculation, chained to demands we cannot meet, reliant on exotic matter we have never found. The contrast is stark. Gravity is effortless. Warp is fragile. Gravity sculpts the universe as casually as wind shapes dunes. Warp must be forced into being, demanding energies that dwarf stars and substances that may never exist. Gravity thrives in simplicity. Warp drowns in conditions. To ask who wins in practice is no contest at all. Gravity reigns supreme. And yet, victory is not so simple. Warp challenges gravity not by matching its dominance, but by daring to exploit its rules. Gravity bends space. Warp bends it differently. Gravity sets the speed limit. Warp finds a way around it. Gravity builds black holes as prisons. Warp imagines bubbles as escape routes. Even if warp cannot win today, its very existence in equations makes it a contender. It shows that the laws are not as absolute as they appear, that the universe may harbor loopholes where imagination and mathematics meet. This tension defines the contest. Gravity wins in the present, in every observation, in every test. Warp wins in possibility, in the audacity of asking whether the universe allows more than it reveals. Perhaps the real question is not who wins, but how the rules themselves evolve. If warp one day proves real, gravity will not have lost. It will have been reinterpreted, its authority expanded rather than diminished. Victory may not belong to one or the other, but to the new physics born where they collide. Victory in this cosmic race depends on how we choose to define it. If winning means being universal, unshakable, and ever-present, then gravity has already secured its crown. Every falling apple, every orbiting planet, every collapsing star is a declaration of gravity's supremacy. It rules without negotiation, shaping the very stage on which all other forces act. It needs no invention, no speculation, no loophole. It is the quiet sovereign of motion, and its authority has never faltered. But if winning means offering a path beyond limits, then warp lays its claim. Gravity confines us. It places the stars at distances so vast that even the speed of light seems slow. Warp whispers of escape, of voyages that leap across those gulfs not in centuries but in hours. It is not a law proven in the laboratory, but a possibility glimpsed in equations. Its power lies not in demonstration, but in potential, in the audacity of suggesting that the universe may not be as closed to us as it appears. In this sense, warp is not victory achieved, but victory imagined. And imagination itself has always been the first step to conquest. The comparison sharpens when we weigh practical reality against speculative future. Gravity is practical. It bends light around galaxies, shapes black holes, and defines the tempo of time dilation. We have measured it, harnessed it, and learned to predict it with extraordinary precision. Warp is speculative. It demands negative energy, exotic matter, and technologies we cannot yet conceive. But speculation is not weakness. Every great achievement in science began as speculation. Flight was once fantasy. Splitting the atom was once inconceivable. Reaching the moon was once myth. Warp too may someday leave the margins of mathematics to join the ledger of reality. For humanity, the winner of this contest matters less than the race itself. Gravity holds us where we are. Warp tempts us to go beyond. In the present, gravity is victorious. But in the future, warp may redefine what victory means. Perhaps the truest outcome is that both win, gravity as the eternal framework, warp as the dream that pushes us to challenge it. Together they shape our destiny, one by enforcing the limits of the cosmos, the other by daring us to imagine pathways through them. In the end, the question of who wins may not have a single answer. Gravity is undefeated, its victories written into every orbit, every collapse, every ripple of space-time we observe. It is not a force we can outmatch. It is the framework of reality itself. To deny its supremacy is to deny the universe as it is. Warp cannot dethrone gravity. At best, it can ride upon its rules, twisting them into new forms, finding cracks where possibility hides. And yet, the very existence of warp in theory changes how we see gravity's authority. It suggests that the cosmic speed limit is not an unbreakable wall, but a carefully guarded threshold, one that might be approached from a different angle. Warp does not overthrow gravity. It challenges it to reveal more of itself. If gravity is the law, then warp is the exception that proves the depth of that law, a clue that the universe's story is not finished. For humanity, the outcome of this contest will shape our future. If gravity alone defines our fate, then our voyages will be confined to the slow crawl of light speed, our exploration measured in centuries and millennia. The stars will remain distant, their light arriving long before we can. But if warp or wormholes one day prove possible, then the galaxy becomes a map of destinations, not barriers. Our descendants could cross to other suns in the span of a single lifetime, weaving the cosmos into a network of human presence. Perhaps the real victory lies not with gravity or warp, but with the physics yet to be discovered. Just as relativity deepened and transformed Newton's vision, a future theory may reveal pathways we cannot yet imagine. In that framework, gravity and warp may no longer appear as opponents, but as aspects of a deeper unity, one that shows us how to live with both limits and possibilities. Until then, the race continues, not in ships streaking across galaxies, but in minds daring to dream. Gravity holds the crown of reality. Warp carries the torch of imagination. The true winner may be neither, but the synthesis born where certainty meets speculation, where the rules of the universe and the audacity of human ambition collide. From the first time humans looked up at the stars, the dream of reaching them has been bound by distance. Gravity kept us grounded, then carried us into orbits and beyond, shaping every step of exploration. Relativity then revealed that space and time themselves were woven together, that speed had a limit, and that gravity was not merely a force, but the curvature of that fabric. Against this backdrop, warp drives and wormholes emerged as daring ideas, loopholes hidden in the mathematics, promising escape from the tyranny of distance. Now, at the end of this contest, we must ask, what does the future truly hold? The story so far has been one of contrasts. Gravity is real, observable, and universal. It sculpts galaxies, bends light, and slows time with effortless precision. Warp is speculative, fragile, and demanding. It lives in equations, but not in laboratories. It tempts us with journeys across galaxies, but chains us with requirements we cannot yet meet. Wormholes stand between the two, natural solutions in relativity's framework, but unstable, dangerous, and reliant on exotic conditions. Together, they paint a picture of a universe both generous and restrictive, offering glimpses of shortcuts, but demanding prices too steep for us to pay. And yet, humanity has never been defined by acceptance of limits. Every age has declared some frontier unreachable, only for the next to prove otherwise. The mountains, the seas, the skies, and finally space itself. Each seemed insurmountable until persistence and imagination overcame them. Faster-than-light travel may appear impossible today, but impossibility is often only a measure of the tools we have, not the tools we might one day create. The future of motion in the universe may belong not to gravity's certainty or warp speculation alone, but to new physics waiting to be uncovered. Already, hints suggest that our understanding of space-time is incomplete. Quantum theory and general relativity, the twin pillars of modern physics, remain unreconciled. At the smallest scales, space-time may not be smooth but grainy, foamy, or pixelated, with geometry fluctuating like waves on the surface of the sea. At the largest scales, dark energy and dark matter hint at forces and substances we cannot yet explain. In these unknowns may lie the seeds of technologies as unimaginable to us now as rockets would have been to the ancients. Thus, the contest between gravity and warp is not a final battle, but an opening act. Gravity shows us the rules. Warp shows us the loopholes. The future may reveal a new synthesis, a deeper law that unites them both and points toward pathways we cannot yet describe. Whether those pathways permit faster-than-light travel is uncertain. What is certain is that the universe is not finished revealing itself, and neither are we finished searching for ways to move within it. If humanity's future remains bound by relativity as we know it, then our path to the stars will be slow, deliberate, and patient. We will rely on generation ships that drift across light years over centuries, carrying communities who live and die among the stars without ever seeing their destination. We will master hibernation technologies, slowing human lifespans so that voyages measured in hundreds of years become survivable. We will send robotic probes, tireless and efficient, to scout ahead, bridging the gulf with machines long before humans follow. In this future, gravity remains the silent ruler, enforcing the light speed limit as absolute law. Exploration continues, but its pace is measured in lifetimes rather than moments. The stars remain distant, and patience becomes our greatest engine. But if deeper physics one day opens the door, the story changes entirely. A single discovery could redefine motion in the universe. Just as relativity expanded Newton's laws, a new synthesis might expand relativity, showing us how to tame space-time in ways that today appear impossible. If negative energy proves real and controllable, if wormholes can be stabilized, if warp bubbles can be shaped and sustained, then faster-than-light travel shifts from speculation to engineering. The universe itself would shrink. Galaxies that now seem unreachable could become destinations. Humanity's timeline would compress, transforming journeys that take centuries into voyages lasting days. Such a shift would not only change exploration, it would redefine civilization. A warp-capable species would not merely colonize planets. It would weave a network of worlds, cultures, and economies across the stars. The night sky, once a barrier, would become a highway. Time and distance would no longer confine our destiny. The very meaning of home, community, and identity would stretch to scales unimaginable today. Gravity would still shape the cosmos, but humanity would no longer be confined by its pace. Between these two futures, one bound by patience, the other liberated by physics not yet discovered, lies uncertainty. We do not know which path awaits. Both are plausible. Both rest on truths we have already glimpsed. The slow future relies on technologies we are beginning to master: nuclear propulsion, fusion power, artificial intelligence. The fast future relies on mysteries we do not yet understand: exotic matter, quantum gravity, the full nature of space-time. Each path is a continuation of the human story. One is steady endurance. The other is sudden transformation. The choice between them may not even be ours. The universe itself will decide, through the laws it hides and the truths it reveals. We can search, experiment, and dream. But in the end, whether warp or wormholes can exist depends not on our imagination, but on the fabric of reality itself. Our task is to look, to question, to test, and to push against the limits until they reveal themselves, whether they yield or hold firm. The race between gravity and warp has carried us through dreams and equations, through realities we can measure, and possibilities we can only imagine. Gravity stands unchallenged in the present, shaping stars, galaxies, and time itself with effortless command. It is the universal constant, the sovereign ruler of motion. Warp is the rebel, the contender born from imagination and mathematics, whispering of loopholes and hidden pathways. One is certainty, the other is hope. Together they frame the question that has haunted us since we first looked at the stars. Are we bound to the pace of light, or can we one day escape it? The answer, for now, belongs to gravity. Every experiment, every observation, every voyage confirms its rule. Warp exists only as possibility, chained to conditions we cannot yet meet. And yet the dream persists. Humanity has always defied limits, turning impossibilities into milestones. Flight, electricity, nuclear power, space exploration, all were once fantasies. Warp may join them, not today, not tomorrow, but in a future shaped by discoveries we cannot yet foresee. If that day comes, the universe will change forever. The stars will no longer be distant lights, but destinations. Galaxies will no longer be unreachable, but familiar. Humanity will no longer be a species confined to one world, or even one system, but a civilization scattered across the cosmos, bound together by highways of space-time itself. Gravity will not have been defeated. It will have been reinterpreted, its rules expanded into a deeper law. Warp will not have broken the universe's order, but revealed a broader harmony within it. And if that day never comes, then the stars remain far, but not unreachable. We will still explore, still build, still reach outward at the pace nature permits. Gravity's rule may slow us, but it cannot still our ambition. The cosmos will always call, and humanity will always answer, whether in centuries-long voyages or in leaps across loopholes. The contest is not truly about victory. It is about vision, about whether we accept the universe as we find it or dare to imagine it otherwise. So who wins, gravity or warp? Perhaps neither, perhaps both. Gravity rules the universe, warp challenges it. The real winner is the new physics that may emerge where they collide, a truth not yet revealed, waiting in the depths of space-time. Until then, we are wanderers on the edge of knowledge, standing beneath the stars with questions as vast as the night sky. If space is ever to yield its final secret, it will not be as a boundless canvas. It will be as a cosmic mosaic, painted one discovery at a time.